Today, we're going to be making the the cap for the top of the screwdriver. Last week, we went ahead and we made the body, like you see right here, where we went ahead and drilled holes down through the center of the part so we can stick this magnet down in there and permanently attach the magnet to the screwdriver body with this roll pin right here. So the roll pin keeps that magnet inside there, holds on to the bits, and then also magnetizes the screw that it's holding in the tip once we do that. So we're going to focus on this part here today, part number 2. So let me grab my engineering drawing for that. Looking at part number 2 right here, you're going to see we have a thread milled inside this cap. So we have a 7/8 14 UNC 2B thread that goes 0.675 deep. Because we're thread milling, we don't actually have to have a thread relief. That's kind of a benefit of cutting a thread with thread milling. You don't actually have to have a thread relief in the bottom of your thread. So this kind of shows how that works here on the section view on this drawing, where the thread actually just stops here at the bottom of the cap after it goes 0.675 deep. Notice also, this is a flat bottom hole. So we can't make flat bottom holes with drills. So we're going to have to use an end mill to pocket this part in order to create that flat bottom hole. And looking a little bit more on this project here, we see that we've got a 257 hole at the top of the cap, so we'll use an F-size drill bit to drill that. And then we have basically radius of 0.175 around the outside of the part right here. We have 50 thou radii on the inside of the part right there. And pretty much we're ready to go ahead and make this part like you see right here. So how do we do that? We use a manufacturing routing in order to make that part. So we look at the engineering drawing and we come up with all the steps to make the part from bar stock to first article inspection, to pretty much wash it, clean it, and then ship it out for that first article inspection. So we have 7 different steps we have to go through in order to manufacture this part. Looking at the first step, operation number 10, that was done on a bandsaw in our case. The routing says to use a cold saw, but we wanted to go ahead and cut multiple parts at once. So we went ahead and used the horizontal bandsaw over in the advanced lab to kind of cut the stock to length right there. So we don't have a video of that today because we were providing stock for all the students in the face-to-face labs because we're not having the students cut them individually there. So we've got our 1.0 inch diameter extrusion that was cut to a 1.75 inch length of cut, plus or minus 30 thou on that bandsaw. So that's been done for us, operation number 10. However, we have to now move on to operation number 20, where we're going to go ahead and face mill the first side of the part. We're going to drill a hole in here, a pilot hole. We're then going to contour the outside diameter, and then we're going to bore the inside diameter to the threads a little bit larger than the thread's minor diameter, because 75% thread engagement. We're going to chamfer it and then helical thread mill that 7/8 14 thread. So let's move over to CNC mini mill number 3 in order to do this. Welcome to CNC mini mill number 3. We just powered this machine on. So I have to get the table in front of me. So if you remember, we can go to handle jog mode, and we can move the x-axis 0.01 of an inch and jog the table over like you see right here. So looking at this, we have a soft jaw set here in this machine. So these chick one-lock vices that we have here have removable jaws, and we have a set of aluminum jaws in here that we've cut the profile for op number 1 and op number 2 in these jaws. Now, what I've got to do before I put my stock in the machine, I want to go ahead and deburr the saw cut sides right here. So if I was to go ahead and locate the part in the machine with these burrs sticking up on these edges, it's going to sit in the vise a little crooked. Even though it's got a soft jaw or contoured vise, nested jaws, it might still sit a little crooked. So we're going to take our file, remember files work in one direction, and we're going to file away from ourselves, removing all the burrs from the outside edge of this workpiece right here. So once we've got these burrs deburred on this one side, I'm not going to worry about deburring both sides because it's going to stick up out of the jaw and we're going to face mill it off right now. So I'm just going to concentrate on basically making sure that one side is fully deburred before I put it in the vise right here. One more second. All right. Now that we're fully deburred, I'm going to go ahead and put my part in the vise. So I put it down here in the soft job, and I'm going to use my torque wrench to go ahead. I tighten it by hand first, but I'm going to go ahead and use my torque wrench to go ahead and torque my vise, the correct 25, or what we got this one at 10 foot-pounds. I was going to say 25, but this doesn't require that much clamping force. So we got 10 foot-pounds right there of torque that we placed on here, which equates to a certain amount of force on that vise right there. Now that it's in there, I just tug on it just in case, right? Just in case. And I want to use my dead blow hammer to tap it down once or twice there so it's fully seated on the bottom datum surface. Now that my part is loaded, I close my doors, I go to my list program, and I just double check that I have the appropriate program pulled up. You'll see it says SD cap op number 1. So if it wasn't, I could go to list program and go select a different program in here in the control. But the program in my memory is that SD, which stands for screwdriver, cap, op number 1, program number 148. So we're going to go ahead. Op 1 is in basically the left side of it. Op 2 will be in the right side pocket here. And actually is labeled on the vise which one is which operation right here. So we're going to go ahead, close the door. We're going to go ahead, hit memory, reset, and cycle start, and we're going to start machining this part. So that first pass is kind of a safety pass I programmed in case someone had a long length of cut of stock. So now that we got the face, the top of the part face, we're going to bring in the drill bit. You can see there's not very much clearance for that drill bit. Probably about 1/4 of an inch, and that's it. Good old mini mill. Now that we got that pilot hole, we're going to come in with a 3/8 end mill, and we're going to contour around the outside of the part. So we're just cleaning up the stock on the outside diameter of that part, trying to go ahead and achieve that outside diameter of 0.988. At this point, we're now going to bore the hole for the thread, slightly larger than the minor diameter for that 75% thread engagement. The noise you hear is it recutting chips. Now it's going to grab our chamfer tool, chamfer the outside edge of the part. Then if you remember, all screw threads start with a chamfer, so it's going to go ahead and chamfer the inside of the part as well. This next tool is going to helical thread mill the thread. So it's creating a helical tool path as it comes up and out of the hole. The feed-in speed for this thread milling is 5,089 RPM, so that's the RPM, 5,089. And the active feed rate is 36 inches per minute. So we cut that thread at 5,089 RPM and 36 inches a minute. Remember that. So we cut the thread in multiple passes. It's a sharp tool, doesn't really have a nose radius, right? It's a 60-degree point. And we have to go ahead and cut that in 2 or 3 passes, or 3 or 4 passes, because if we try to cut it all in one, we would break the tool or the tool would chip. It's just too sharp of a corner angle. At this point, it's going to do its lead out. Then it's going to go ahead and send the table forward to the operator. Put the original tool back in, and we're ready to go. So remember, we take our air nozzle, put our safety glasses down, blow out the cap right there. So what we did there, go ahead and loosen the vise real quick. Remember, vise is the quarter turn. Pick this back. I literally can now push my part back, take my part out right here. So what we did there is we went from raw stock like this to, we faced it, we went ahead, we drilled a pilot hole, we contoured the outside to that 988 diameter, we then bored the inside hole right there and then chamfered the part. So you'll see our part's pretty much ready for the next operation. Where do I go next? I don't know. I have to look at my routing. So when I come over here and I look at our routing, we just finished operation number 20. We are now going on to knurl the cap's outside diameter. So instead of this really shiny surface finish, we're going to basically do a process called knurling. Now we have a couple of different knurling tools in this lab right here. We have a coarse knurling tool, which looks like the outside of a Maglite flashlight. I really like that one. It's probably the one I'm going to use. We have a finer knurl, diamond knurl that you'll see right here. They're known as diamond knurls. So the way that works is we have this knurling tool, which is a hardened tool steel roll. It has 2 hardened tool steel rollers right there. And what happens is you're not cutting any material here. You're cold working the outside surface of the part. So you're actually making the part a little bit stronger because you're cold working it. But what we do is we put it in the lathe. We go ahead and we align it up. And we put pressure on it, and then we're going to auto feed away from the chuck off of it, giving it this nice diamond pattern. So literally these 2 rolls that cross each other right there are going to create that diamond pattern when we feed down off the workpiece. Now, if you look, there's also these straight knurls here on this part. A straight knurl is designed more for a press fit. Like on a wheel stud, they might have a straight knurl on it, so when you press it into the hub, it permanently attaches there. So that's what the straight knurl is for. It's not really for like a knob like this. So we're going to go ahead and we're going to go and knurl the outside diameter of this machine surface of the part over here on our lathe. Let me grab my routing, and here we go. Now, what we've got here is we've installed a 1-inch collet and a collet chuck on this lathe. So far, we haven't used collet chucks in this lab. So this collet chuck, when I put the lathe in low gear, this collet chuck expands and expands and contracts based on me turning this wheel. So when I put my workpiece in here, if I go ahead and I go clockwise and I tighten my wheel up, my part, the collet collapses concentrically around that workpiece, and I now have my work holding for this operation. I prefer collets over 3-jaw chucks because they don't mark up your part as much. You just have to have a really tight diameter or a known diameter to work on this collet. So I can only put a 1-inch piece of stock in here, plus or minus about 20 thou on it. That's why we use 3-jaw chucks for most of our projects though, because it allows me to grab anything with any size. And when we're first learning about how the lathe works, we're not making parts the exact size. No one does. It's just not the way that works. So I'm going to put this knurling tool now down on my lathe, right here, and I'm going to go ahead and lock it down in place. I'm also going to come around to the side of the lathe over here, and I'm going to go real slow in terms of RPM. I'm going to go 46 RPM when I'm knurling right here. So I want to be in red gear to be in low. I want to be at 46 RPM. I want to be in reverse because I'm going to feed the knurling tool off the part in that direction right there. So I'm going to feed off the part right there. Now, that leads me to setting up a feed rate right here. I'm going to feed basically at 8 thou right here by going to A. And if sometimes you can't get it to switch, you got to come up here. You got to go, there it goes, back and forth. So I got it in A, and now I'm going to put it back into red gear. It doesn't have any synchros. It's not like a manual transmission that has synchros that help you synchronize the gears. So they're just hard gears, and you got to kind of move the gears around sometimes to shift this thing into the right location. Now, before I cut or turn anything on, I know I got to put my shield on, but I just double check that my knurling tool is going to be able to fit in there without running into my workpiece right there. So you'll see I've got plenty of clearance. So what I'm going to do is I'm going to put my shield down. I'm going to go ahead and turn on the lathe to a slow RPM. The lathe is now turning or rotating. So what I'm going to do is I'm going to bring my knurling tool into my workpiece right there and slightly put pressure on my part. I'm not putting a lot of pressure on this thing. And as soon as I get a nice uniform surface, right about there, I would say, a uniform surface, I'm going to use my auto feed to come up and long feed down my part right here. So you're going to see it slowly walking itself down the part. So we're going to let it do that for a minute or so. You can see it's automatically feeding over here, just very slow because we're at 46 RPM, and we're moving only 8 thou per 1 revolution right there. So it's going to take a little bit of time, but we're forming the part, and we're making that 45 or that diamond knurl on the part. It'll be there in 1 second. Just let it keep going. We'll wash it afterwards with rubbing alcohol, and all the darkness will go away. It'll look great. So we're almost to the end. We'll let it fully come off the part. I could have done this faster. Like if you do it in a CNC lathe, you do it way faster. Just for now, we're learning, so we're going to go nice and slow. Almost there. It's like watching paint dry, right? It's like watching the part get knurled. So we're almost there. I'm going to let it kind of feed off the part completely. Now that we're off the part, I'm going to go ahead and bring it off the rest of the way. So what that did was it left a nice diamond knurl. Let me show you here. So we have a grip on the top of our screwdriver knob. It's really dirty, a lot of cutting fluid in there. So this was actually the finer knurling tool. I didn't grab the coarse one. But here we go. So you can kind of see it was how I fed it basically. It was what made it a really small knurl. But I'm all right with that. So at this point we now have a grip on our surface. I know it's all dirty, but we'll clean up our part at the end. It's always part of it. I forgot to put this pin in right here. So normally we put in this plug when we knurl, and I just didn't crush my part. I was real light on it, and it works no problem right there. So at this point, I don't know what to do next, so I look at my manufacturing routing, and I see that I just knurled my cap's outside diameter. So now I'm going to go face mill the side 2 to the final height, rough my basically tab, and then I'm going to contour it, the radius around it, the 1/8 inch radius, and then I'm going to chamfer the part. So let's go ahead and do that on mini mill number 2 or 3. Because I was just on 3, I'm going to go back to 3. Let's go back. So at this point, we're going to put our part now with the machine sides down. We're going to take care of this top part. What we're doing is what we made is the bottom piece of the screwdriver right here, or the cap. So now we're going to basically face down and make this lug that you can go ahead and put it on your keychain right here. So to do that, you come over here. We have our fixed jaw on this side, so I'm going to get it ready to basically come forward like that. I then tighten it by hand. When it's tight by hand, I'm going to bring in my torque wrench, torque it down. Just a nice little seat it. Whoops. At this point, I'm going to put my face shield down. I've got to change my program now. So I go to list program. I come down and I find 149. Whoops. 149 cap op number 2. So I hit select program, I go to memory, reset, and I double check that it says cap op 2. Now that I'm good to go, I press cycle start, and it starts machining. So what we're doing here is we're contouring around the outside of the part right there to make that lug. So we're working our way in to cut that lug off the top. In order to put the fillets on the lug, we'll end up bringing out a ball end mill to put those 1/8 inch fillets into it. So the lug's roughed out with the regular 3/8 end mill. Now we bring out the ball end mill to go ahead and put the fillets in the corner. After we put the fillets on the thing, we got to go ahead and make sure we don't cut ourselves, so we're going to chamfer it with our spot drill. Then we come around the outside and chamfer the outside. Last but not least, we send the table forward, and we're ready to go ahead and open the doors, blow our part out, and then take it out of the vise. So quarter turn open, push back, take your part out. So we went from basically raw stock to machine part right there in those couple of operations. The only thing that we're missing on this part, we looked with the ball end mill, went ahead and cut the fillets in the part. We're missing the through hole right here, because when I grab my drawing, it's pretty close to that final part right there. So when I look at my routing to figure out how I'm going to drill that hole, I've got to go ahead and drill the cap for the mounting hole using a 257 drill, which is an F-size drill, and I need a jig to go ahead and do this. So a jig is something new that you're going to learn about right now. Let's head over to the drill press. So jigs are designed for more so for drill presses or manual machines. There's fixtures and there's jigs. We've used fixtures throughout this class to hold our workpiece. A jig will actually guide a tool in the right location. What we have right here, this is for the air motor project, but in order to drill these two holes in this wood base like you see right here in the correct location, we would use this drill jig that you see. So what I can do is I can lock the part into the jig. See, it locks in on this edge, and then that edge right there, I lock it down. I now have hardened drill bushings. I could go ahead and drill the holes in the right location in reference to the part. So a jig guides a tool. A fixture holds a workpiece in relationship to the machine's axes. So CNC machines get fixtures, and that's what manufacturing engineers do. They design fixtures to hold workpieces in CNC machines while the parts are getting machined. Well, a jig is beneficial if you don't have basically a set of servos and encoders to keep your track of your position. Like for example, I can go ahead and put this jig anywhere on this drill press, but when I put my part in here to locate it, you're going to see there's a small diameter hole, so I can't put it in sideways like this. It just won't fit. So I can only put it in one way right here. And once I put it in, oops, I keep putting it in and pulling it back out. So once I put it in, I can lock the toggle clamp down and the part's not coming out anymore. I literally now have this drill bushing that's going to allow me to drill the hole in the right location. So the jig is guiding the tool into the correct location. Fixtures just hold parts, and the CNC machine with its encoders and the servo motors have to go ahead and position the tools in the right location. So they used to be a lot more popular, the jigs, but now they're kind of more of a thing of the past compared to a CNC machine when you can program it a lot quicker. So now that my part is in there, I'm going to put down my shield. I'm going to go ahead and turn on my drill press, and I'm going to hold on to my fixture or my jig and drill the hole in the right location. So I'm just peck drilling, real slow. I don't know if there's a 257 hole. The drawing might need to be updated. So at this point, when I turn this off, I got to take my part out. It's somewhat stuck, so we have something for that. I have that in my pocket actually. Grab it. The top of my screwdriver. So I can put the top of my screwdriver and grab it real quick. We have a tool to pull it out of the jig afterwards. But what the jig did is it basically located this hole in the correct location on this lug right here. So now we have a hole in the top of our screwdriver to go ahead and attach it to maybe a keychain. Should we check to see if it fits? So if we look, our threaded cap easily threads onto the part right here. But I'm not done with my part yet. Let's go ahead and move back over here and check the routing. So when I look back at my routing right here, you're going to see once I drill my mounting cap, I'm going to deburr and wash with water and then perform a first article inspection. So instead of washing mine with water, I'm gonna grab some IPA real quick and clean up my parts before I put them together. Now, one thing I forgot to do on my routing is I forgot to read the rest of the instructions after I drilled the hole for the jig. So let me go back and look at that real quick. When I go back and I look at my routing, it says deburr and wash. So I did the drill the mounting, but I haven't deburred with my rotary deburring tool. What happened is when I created this hole, it left some burrs on the top of the hole. You can kind of see them. So I'm going to grab my deburring tool and go roundy round like I do and make a nice little chamfer on the outside of my hole there. So with that, we pretty much have the part now finished being machined. So I can go ahead, put my cap, my thread milled cap on top of my screwdriver. Let me just show you real quick. We have a flat bottom hole and we have a thread milled in the bottom of this cap without a thread relief right there. So I just wanted to show you the difference between a thread relief and one without a thread relief there. So at this point, we have the full assembly done for this screwdriver. So now I can put it on my keychain and never lose it. So the last step would have been a first article inspection, but I feel that you've read enough calipers through your virtual labs, through pictures and videos and so forth this far this quarter. So we're going to jump on to the cost analysis for this part of the project. This is something we do. We're going to look at the different routing, or the routing for the body and the cap, and we're going to figure out how much manufacturing shop time, or basically machine time, we have into this part. So we're looking at about $120 an hour for machine time, and that's including electricity and pretty much tooling and everything that we've got.
32 minutes.
So 320.
32 minutes.
32 minutes of machine time so far. We're gonna look at the individual machine times as we go through it. We're gonna look at the routings and figure out exactly how much time we put into this product through all of our different routing steps. So join me now, and we're gonna go do that. Come on, let's go.
Now that we went ahead and seen how the body and the cap for the screwdriver have been manufactured step by step by following through the routings over the past 2 virtual labs, we're going to go through and figure out how much does this assembly actually cost to manufacture in terms of raw materials and also machine time associated with the screwdriver's manufacturing operations. So when we're talking about production costs and manufacturing costs, we really need to think about 3 different things right here. We need to think about the manufacturing overhead, the direct materials involved to go ahead and produce that part, and any of the direct labor that was involved to make that part there. Let's talk about each one of these individually a little bit before we actually estimate the cost. So that manufacturing overhead, those are expenses that are not directly involved with the direct costs of manufacturing. For example, engineering might be an example for this. Not the manufacturing engineers that are actually on the floor working directly with the screwdriver as it's being processed, but we're talking about the engineering staff, the design engineers that are housed in there. They're salaried. No matter what, they're going to go ahead and get their salary if we make 0 parts or if we make 1,000 parts or however many we make. We still have to pay the engineering staff to be on staff. Now, if you think about it, anything that has to do with overhead, it doesn't have to, it's not directly related to production costs right there. So they're indirect costs to support manufacturing. You need a building. So you've got to either pay rent or property tax if you own the building outright, right? So you got to pay into the utilities and maintenance for that building. Supplies, if you think janitorial supplies for the bathrooms, everything. Taxes, insurance on that building, depreciation, and you got to also pay payroll for the people that are indirect, any of the indirect labor. You got to pay all that payroll to keep the shop open. That's just to keep to open the shop, basically, right here. All this overhead. So the shop manager, the supervisor, shipping, receiving, warehouse, inspection, and maintenance employees. Those are all more overhead costs that if we make 0 parts, we still have to pay this. We still have to keep the doors open. So this is known as keeping the doors open, this overhead. Now, we're not going to worry about manufacturing overhead when calculating our screwdriver manufacturing costs. I accidentally wrote air motor, but screwdriver manufacturing costs right there. We're basically not going to worry about overhead too much. We're going to look at our direct manufacturing costs today. So to manufacture that screwdriver, we have to go ahead and account for all the raw materials in there. Now, when I'm talking raw materials, I'm talking raw material or raw stock to manufacture the parts we made in-house. We also have to get the raw materials needed to assemble the part, right? Or the standard parts out there needed to assemble the part. So really, this thing had 4 parts in the assembly drawing, but there's 6 parts overall when we add the bits that go with this screwdriver right here. So looking at the different part numbers right here, these are our suppliers. We have either MSC or Home Depot, actually, where we get our magnets. We order a bunch of them on Home Depot online. But you're going to see here, for example, if I was to go ahead and need the cost for this slotted spring pin when I go to order it, I can click on that link right there. And that brings me to the website, just kind of show you where we sourced all of our parts for this. So here is our roll pin. So they're basically $1.06. Basically, if you look at them, they're 16 cents a piece, right? So we're looking at that per 100 of them. So that's how we got the cost for this. So we went ahead and we looked up based off of our suppliers' costs to get the raw material costs, because they're from our supplier. I was gonna say the standard parts, but the raw material or the standard parts costs right there. So I'm gonna close that one down. So we've got 2 pieces of bar stock right here, the hex stock and the round stock. Normally I don't buy it from MSC, but you can source this from MSC if you wanted to. I use Coast Aluminum that's in Fresno in order to get our 1-inch bar stock. But if you see, here's a 72-inch long piece of aluminum bar stock. They're $106 a piece. So we figure out our cut length and however many we can get actually out of that bar to come up with that raw material cost. This is not where we got the cost for our cost analysis today. I have a different cost for the raw material for you based off of our Coast Aluminum supplier, which gives us a little bit better deal than the MSC for bar stock there. Now, so you're going to see we got the hex stock, we got the round stock. Let me just click on that real quick. The round stock also comes, I believe, it's 72 inches long here. When we order it from Coast Aluminum, we get a 12-foot extrusion. So actually MSC is taking those extrusions and cutting them down for shipping, really. So we're going to get we ordered in a 1-inch diameter, 144 long, and then chop it up right there. So looking at this 1-inch diameter stock, it's 72 inches long. It's about $42.35 right here. So for that 72 inches of it. Now, looking at kind of the standard parts that just go together, we also have that screwdriver bit, as you can see right here. So any 1/4-inch drive, hex drive, will fit into this screwdriver assembly right there. So that bit was only 77 cents right there. So that just kind of shows you where I'm getting my raw material cost from. So I look for my suppliers, how much it costs, and I've got basically my raw material cost. Now, if I scrap any parts, I still have to pay for raw material. So if I scrap a screwdriver body, I got to pay for that hex stock. If I scrap a screwdriver cap, I got to pay for that round stock still. So looking at this, hopefully you understand that where our raw material costs are coming from in this cost analysis. They're coming from the costs from our suppliers. Now, we're going to switch gears a little bit. So that's raw material costs. We talked about raw materials. We talked about manufacturing overhead, but there is basically overhead directly related to manufacturing, and that's going to be our shop time or our manufacturing cost right there. So it's again not air motor, it's screwdriver project. So when we're talking about our direct overhead related to the manufacturing cost, it's the shop rate there. So the shop rate, every shop has some sort of shop rate, and that's calculated using a recent range of actual direct labor hours and costs, as well as tooling that you're going to be using through that. But some shops put their tooling costs into their direct labor right there. If it's a specialty fixture that you're manufacturing for a job, that's going to be completely different. The customer is going to pay for that specialty fixture. However, if we're using just general work holding like vices, 3-jaw chucks, we're using standard cutting tools, a lot of that tooling is actually put into your shop rate. Now, around here, CNC shop rate, it's about $180 an hour. It depends on what shop you go to and so forth. But we're going to assume $180 an hour for our CNC shop rate. Then we're going to have a different shop rate for our manual labor. So we don't have to worry about the high-tech machine tools and the expensive tooling when we have our manual labor shop rate. So our manual labor rate's $120 an hour. And that's going to be whenever we're maybe assembling. We just have the technician assembling parts in the assembly cell and so forth. So manufacturing shop rates are basically anything that's where you have a technician or an operator doing direct labor on the part, the shop rate comes into play here. So we're going to take the shop rate and the raw material costs along with the times that it takes to go ahead and manufacture each step in the routing to figure out a cost here now. Now thinking about it, I went through and timed the different operations. So basically I went through without me doing extra spiel, right? So it's not the amount of times to manufacture it while I describe everything. It's just the amount of time that it would take the technician to put the part in the chuck or put the part in the work holding, perform any of the operations that need to be performed on it in that step in the routing, then take it out of the work holding. So it's basically work holding to work holding, timing it. Now, we're not really worried about work in process and moving it around the floor in this exercise. We're just looking at direct costs here, so the direct labor and then the part material costs. Now, a lot of shops will record this time, this direct time in their routings. And they'll basically use barcoded routings or RFID, radio frequency ID tags, to go ahead and track parts throughout the different operations in a facility. And that way they can get the real time or the real cost of the part. In fact, a lot of technicians will go ahead and have a barcode right there at the station. They can scan in the step that they're doing. So they kind of have a start time. And then they'll figure out, it'll kind of have a time, then how much time it took to produce that batch of parts. So for right now, this routing is for a one batch of parts. And we're going to basically assume that we didn't scrap anything along the way. However, if you scrap something along the way, you've got to add up all of that direct labor or that shop time that's on that you put into that part before you scrapped it. That's why you don't wait to the last minute to inspect a part. You like to do in-process inspection because it's going to go ahead and cost your company a lot less by finding defects in the process as opposed to finding defects when you're all done making the product in the final assembly stages. You don't want to go ahead and wait till final assembly to go ahead and take care of that. In fact, you think about it, that $180 an hour right there is $3 a minute, right? For CNC machine time, if you think about it. So, I mean, if we scrapped it right here after op 2, if you think about it, we already have 3 minutes in there, 3.5 minutes in there, right? So if we're thinking about that, we already have $9 plus the 9. So we have 13.5. So we have a little over $10 into the thing, right? So we wouldn't want to go ahead and keep processing it through that if we have to basically scrap it at the end. That's why we got to go ahead and perform in-process gauging and inspection during the manufacturing processes. So when I go through this screwdriver body and I look at all the different times, I end up with 54 minutes of direct labor. So 54 minutes of manufacturing time to make one screwdriver body. Now, this is a little exaggerated because we can make this screwdriver body in a lot less steps and a lot less time, but this was more of an educational project to show you how we do cellular manufacturing. We set up machines to cut parts or set up machines to basically perform only one operation and kind of go from there. So it was more of a learning experience. It wouldn't take 54 minutes to make this in the real world. On a live tooling lathe, I could probably make that screwdriver body in about 2 minutes, maybe 3 minutes. Oh no, with the engraving. So probably more like 4 or 5 minutes with that. And the engraving is even slowed down, and the feeds and speeds are slowed down heavily in this assignment on the CNC machines. Because again, we're learning how the process of manufacturing from start to finish here in this class. So realize that's, if we were to make this part in the real world, it would not be this expensive is what I'm getting at. But it took 54 minutes to make the screwdriver body for us, right? And it took 24 and a half minutes to make the cap as we went through there. Now I'm talking about first article inspection time, deburring and washing. We're going to call all of this at our CNC shop rate today. Some of these steps might not have been charged $180 an hour shop rate, but you know what we're going to end up doing is we're going to just kind of simplify this cost analysis. I want you to think about time in terms of money, because time is money. So, and that's really what I want to get across to you. And I want to get across to you that scrapping things is not a good thing because it costs a lot of money for that company. And that's the less money that company makes, the less you make maybe with your bonus at Christmas time. So at the end of the year. So looking at this, we're going to determine, so we got 24 and a half minutes and we got 54 minutes right there for the two parts we manufactured in-house. Now, we're going to look at this right here. This is our cost analysis worksheet. We're going to fill it out together here. And the way it works is normally we do a production run for the lab. We look at however many we made in that lab class, which is usually 24 workpiece blanks. Then we keep track of our scrap rate. We're between about a 10 to 15% scrap rate in this class, which is very, very high. But again, it's a freshman manufacturing class, right? We're learning how to make things on the CNC mills and the lathes. So what we're going to do is we're going to just fill it out for one and pretend and basically have a 0 scrap rate for today's exercise. All right, you're all mechanical engineers and manufacturing engineers, industrial engineers, aerospace engineers. You have basically a background in math. So I guarantee you could add in scrap time and costs after this if you had to. But looking at it right here, so when I come here, we're going to have a 1. Let me go ahead and go a little bit smaller with that. Give me 1 second here. So that's not going to be easy to do right away. So what I'm going to do is I'm just going to put a 1 right there. And we have 0 for our scrap, right? So we'll put a 0 in right there. Now here, the manufacturing time was basically how many minutes. So if we look at that, it was 54 minutes for the body, right? Which is going to be how many hours? Well, what we could do is we could either convert it to hours right now, or we could go ahead and just take it $3 a minute if you want to go ahead and do it that way. I think I'm going to just do $3 a minute right here because it seems easier. Just do 3 times the 54. But to do that, I'm going to go ahead. Actually, no, let's fill this out properly. I think that's better. So I'm going to grab my calc. So start run calc, right? Stop this real quick and move this over here. And so when we take basically 54 divided by 60 is 0.9 hours. So whoops. So what I'm going to do over here, let me go back to annotate. We are going to put in 0.9 hours right there. So we have 0.9 hours for the manufacturing time for the screwdriver body. We have 0 for our scrap time, and we have 0 for our 0 there. Now, when we have to figure out the amount that machine time costs us or our direct labor in the shop, we're basically going to use that $180 an hour rate. This is where it might not be perfect because some of those things like deburring and some of those other operations that didn't involve machine tools, like the clean and wash station, would have probably been the more of the assembly or the regular direct labor, manual labor shop rate. So we probably would have put $120 in for those couple of steps. But I'm just want to show you again a basic cost analysis here. So we're going to go ahead and just call everything on that body and that routing $180 an hour. So when I go to 0.9, I go ahead and times that times 180. Let me go ahead and do that real quick. So when I do that, I have 162. So when we come over here to annotate, let me just go ahead and put that in. So it was a 162 for machine time for that part. So we're good there. I forgot to come up here and look at the workpiece blank. We did one of them at $5.90. So if we were to take that cost of that bar stock, the 72 inches from the MSC, figure out our length of cut on that part, we would end up with about $5.90 for the length of cut of that stock. When you're doing your length of cut, you have to include the thickness of the saw blade. Remember that, because the saw blade's removing the material. So when you're ordering material and when you're figuring out what the cost of the material is, the saw removes its thickness. So remember to include your saw blade's thickness in your calculations for your workpiece's length, and then also for the cost for that. So this ends up being $5.90 right there, right? So we're up to that there. Cool. So the total body cost is going to be $167.90. So that's with CNC machine time and raw material. Now, again, we could probably do that in 4 or 5 minutes on a live tooling lathe, which would greatly reduce the amount of time, right? So 5 minutes on that, about $15 in machine time. So it's about a $20 part, most likely. So, but this is how you figure out part cost. Now, when we have the screwdriver cap here, we only had one workpiece blank. We didn't scrap anything down the line. We're not going to make you figure that out in the virtual lab. So ones and zeros there, which would end up being the stock for that screwdriver was $1.37 right there. So we have $1.37 now for the raw material. We didn't scrap anything. Because we didn't scrap anything, I'm going to go down there and write 0 for my scrap time. And I'm going to write 0 for my hours there. But looking at the manufacturing operation time, I believe it was 24.5 minutes. Let me just go back real quick. 24.5. Yep. So we're going to go ahead and put in 24.5 in there right now. So 24.5 minutes. When I come back over here and I clear my calculator, so let me just hit calc again. So I take that 24.5 and I divide it by 60, right? I end up with 0.408 minutes right there. So I'm going to do 0.41. So we'll go ahead and annotate that. 0.401, 0.41, sorry. It was 0.408, so 0.41 is what we're going to go ahead and do for the amount of hours. And I times that by $180 per hour on our shop rate. And I end up with machine time of $73. We could probably make that a lot quicker too, I guarantee it. So, but $73.50. So my total cap cost would be $74.87. So $74.87 right there. Now, we had one spring pin. We don't scrap these, right? We get these from our supplier. We got one neodymium magnet. We have one screwdriver bit, Phillips, and then one standard screwdriver bit right there. So basically we ended up with our 16 cents, right, for this one. We ended up with our $1.08 for this one. We ended up with our $1.07 for this one. And then we ended up with our 99 cents for this one. So when I go ahead and I go to my calculator and I take 16 cents plus $1.08 plus $1.07 plus 0.99 or 99 cents, I get $3.30 right there. So I'll end up with $3.30 for those parts. I'm going to go ahead at this point, and the assembly time, if you remember Operation 150 assembly time, we go all the way back up here. I forgot what it was. Come back up here. Find that real quick. My assembly was 2 minutes. So what I'm going to do here, I'm going to go ahead and put it in 2 minutes. Grab my text tool for that. So 2.0, right, minutes. And when I go ahead and I do my calculator, 1 over 30 is like 0.03 something, but 2 divided by 60 is 2 divided by 60 is 0.0333. Should have known that. But we're 0.033 repeating, right? So we're going to do 033. And when I go ahead and I times that by the $120 shop rate, so 0.033 times 120, I end up with basically $4 in assembly time. So when I take that $4, my standard parts and assembly total right there was originally I had $4 and then I had the $3 and I forgot the other price. So let me just go ahead and add that up again 1 second. 116 cents, 108 plus 107 plus 99 cents, $7.30. So assembly and standard parts cost us $7.30. So when I take that $7.30 and I add the $162 to it, oops, I had the 100, take the 730, and I'm going to go ahead and I'm going to add the 167.90 plus, so the total body cost plus the total cap cost, which is $74.87. I'm at $250 for this screwdriver. This thing's expensive, right? So we need to either figure out a better way to manufacture this screwdriver or go out of business most likely, because I don't think anybody's going to pay $250 for our American-made screwdriver. So we would have to maybe somehow change the way our routing is and come up with a faster way to make this part if we wanted to stay productive and sell this product right here. But again, we could probably make it in 4 or 5 minutes on a live tooling lathe and be done with it. And that would basically be 100% less, right? Cost on that. But hopefully you understand a little bit about manufacturing costs. That was the goal. The Industrial Advisory Board, when we were creating this class, wanted you to think about manufacturing and cost because they go hand in hand. So when you're designing something, you got to think about the cost when you're designing it, manufacturing costs as well. So just think about it. Is it going to be worth putting it on, basically spending this much time on a machining process in order to get that part done? And you can basically look at the different machine process costs, the amount of, or basically the shop rate for like EDM, and we get to that in IME 146, which is electronic discharge machining. If you look at the shop rate for some of those non-traditional manufacturing processes that we're going to get into later on in the next class, and you look at the prices of a conventional machining process, the shop rates, they're going to differ. And that might make a difference in the process you select downstream as well, just by getting it done or figuring out in your design exactly how you want to design something because you know that it's going to keep the costs down overall. So that was the last virtual screwdriver lab for us, or virtual lab set for our 4 virtual COVID labs here that we were doing. So hopefully you've learned a little bit about the costs there, and you've learned a lot about manufacturing throughout the quarter here. And what I'm going to do is I'm going to go to the last slide. If you ever have any questions about manufacturing throughout your career here at Cal Poly, or even after you graduate, you can always shoot me an email. You know my email's on Canvas there, or you can stop by my office hours and I'd be more than happy to answer any questions. But have a great day, and we'll see you around.